Okay, so yeah, thanks for joining in. Um, and this will be I guess, our last lecture together before the final exam. So I thought I'd just spend some time going over kind of the topics for the exam, and then if you have questions, go ahead and ask. I'll try to clarify. All right, so. This is what I have planned. Okay, so the final exam will be taken via Gradescope, and it will be 1 hour and 50 minutes total. We'll have 2 live exams on Friday, September 11th, and you can either take it at 1 o'clock or at 10:10 p.m. and we'll proctor via Zoom. So let's see. Okay, the first one will be MLE, maximum likelihood estimation, but it will be for a univariate probability distribution. Okay, and so I have an example in lecture 3.2 where let me see if I can find it here. You can look up in lecture 3.2. Oh, here it is. Yeah. So in these slides, it's in the maximum likelihood estimation review. There's a PDF. This one's a Bernoulli one. So there's one unknown parameter theta, and given the data, you find the kind of the probability of all of these things, and then you maximize that. And so so it'll be something similar. I'll give you either a PDF or a PMF. Okay, and the PDF or PMF will rely on 1 or 2 parameters, and what I'll do is I'll provide some values that are drawn from this distribution, and based on that data, you'll find the maximum likelihood estimate of the parameter based on the data. And so to kind of keep things simple, if the distribution uses 2 parameters, I will designate and say one of the parameters is fixed, and then you'll only have to find the MLE of 1 parameter. So for example, so there's different distributions that use just 1 parameter, things like, like the Bernoulli distribution, Poisson distribution. And then there's other ones that use 2 parameters, like binomial and normal and, beta and things like that. And basically what I would do to kind of keep things simple for you guys is I would say if it's a distribution of 2 things, I'll say treat this one as fixed and go off of that. Okay. Then there'll be a Bayes classifier problem. Okay. And so, all of these problems were written to with the intention of it being a pen and paper exam. And so these will all be kind of pen and paper problems. And so the Bayes classifier will be similar to lecture 4-1, where I had like the different bags of marbles from the different factories. Okay, so this is the example. Okay, where you get some training data, and you have kind of the summary information from the training data, and based on that, you'd have to calculate the likelihood, calculate the prior, and then and get the posterior probabilities for each of these things. Okay, and so it'll be some kind of problem. It's not going to be the exact same thing as the bags of marbles from different factories, but it'll be in a similar vein there. Okay. And then you'll have a problem with SVM, and you'll have pictures of SVM results, I'll say, for data in 2 dimensions. So you'll have two-dimensional data, and then and it will be labeled, you know, these are the you know, class 1 and class 2, and there's going to be kind of some boundary lines drawn, right? So and then and I'm going to ask you, you know, match each picture to the command. Okay, so it'll be kind of like the homework. So in the homework, you know, you had different SVM results, and you had to kind of talk about what the gamma and cost parameters and their role. And so here you don't have to do any explanation, you just have to kind of match it. And so if there's something where the borders are really kind of squiggly or something, that probably corresponds to a high gamma. And if things are, you know, are less so, it probably corresponds to a lower gamma and things of that nature. And so I'll match up the and I'll have different cost values and different gamma things, right? So there's not going to be like 9 like the homework, because that would seem sort of arbitrary to perfectly match up. So what I would do, yeah, there'll probably be 6 pictures and 6 commands or something, and you'll line up probably, yeah, 5 or 6 pictures, 5 or 6 commands, and you'll line them up. And, you know, if you're not sure, you can hedge your bets and use the same answer for more than one answer or something like that. But it'll be kind of a match the command with the resulting picture. Yeah, it'll be kind of a, you know, low gamma with low cost, low gamma with high cost, high gamma with low cost, high gamma with high cost type of thing. And for radial basis, and then probably I'll also have like kernel linear or something for you to distinguish. All right, and then I'll have a K&N classifier, and this one's intended to be pretty easy. I'm going to provide kind of a picture with on a grid, okay, and the picture will be labeled, and there'll be points in the graph, and then there will also be a test point on the graph. Okay, maybe I won't draw. Okay, I'll provide a test point. Provide a test point. Coordinates. Okay, and then so what you will do is you will have to classify the point as either category 1 or category 2 based on k equals 1, k equals 3, k equals 5, etc. Right? You'll probably be able to do this visually without any coordinates and without any calculations. You just kind of say like, all right, if I put this point here, what's the 1 nearest neighbor? What are the 3 nearest neighbors, and things like that. You know, if you're not sure, you can do calculations to kind of make sure that this distance is less than that distance. But I imagine most of your visual processing can estimate distances fairly well, especially if it's on a grid. So that's going to be the K&N classifier. Should be that one should be an easy problem. Okay. We'll also have do k-means clustering. Okay. And I'll provide a small data set, maybe around 6 points or so. And I'll have current assignments for these, kind of the thing. And then you'll do kind of one complete iteration of k-means clustering, which means you'll recalculate the centroids based on the current assignments, and then you'll reassign the points to the closest centroid. And that will be that. Okay, so pretty simple, pretty straightforward. The EM algorithm, this one, I'll provide a few data points in 1 dimension, and then I'll also provide the formula for the normal PDF, and you will do half of the EM algorithm in that you'll calculate the membership weights. I guess I'll provide the few points, calculate the membership weights of a few points given their value, the current estimate of the mean and standard deviation, and current membership weights. Okay. So, I'll kind of provide you all of the information that you need, and then you'll do the you'll perform the EM algorithm there. Okay. And that's that. And then the last one will be PCA. I'll give you a small data set, maybe a 6x2 or a 5x2 matrix. And then I'll also provide the 2x2 covariance matrix. And I will also provide the results of eigen on the covariance matrix. And from there, you will identify the first principal component direction, and then you'll project the data onto the first principal component direction and report what the results are. And that'll be it for PCA. So it's very much kind of like the homework that's been assigned for this week, homework 6 for PCA, where you kind of do eigen and you project the data onto it and things like that. So I'm just doing kind of like bits and pieces out of your homework and stuff, but all kind of in a pen and paper form. And then the last bit will be conceptual questions, which will be kind of open-ended conceptual questions that you'll just short answer free response that we'll grade. So it shouldn't be too bad, but that's that. Okay, are there any questions? Is good? Okay. All right. Well, so I'll post this. I'll post this document. Please don't share this document with students who aren't in our class, because in the future I might change the questions that I ask. I don't want students in the future to complain about, how you guys got different questions or your questions were easier or whatever. So this is that's what you'll have. Okay. All right. So for today's example in class, I thought I would do kind of an example of PCA, kind of a neat application of it, and this is not something that we do in real life, but it is something to kind of illustrate how this concept of dimension reduction can be applied into different situations here. So this is going to be, I'm going to use a package called Imager. Let me okay, so I have a picture of Audrey Hepburn, and so every time I show this, people are like, "Who is this person?" So this is Audrey Hepburn. She was an actor in I don't know, the 50s, 60s. This is kind of an iconic picture from a movie called Breakfast at Tiffany's. 1961 film with Audrey Hepburn. Okay, written by Truman Capote, and anyway, the famous one of the famous images is her at this restaurant with kind of this smoking stick. and anyway, so this is it. Okay, it's a 634 pixels by 791 pixels. Okay, so I'm going to go ahead and I'm going to load up the image using this package Imager. And what that does is it brings in the image as a big array. 634 pixels by 791 pixels. Technically, it allows for things like GIFs in that you can have multiple frames, okay? So we have one frame, and there's 3 color channels, red, green, and blue, okay? So it comes in as this big kind of four-dimensional array. But in a gray image, the red, green, and blue channels have equal values. So I'm going to just keep one of them. And so I'm going to just reduce this to one matrix that is 634 by 791. Okay. So I just have a big matrix, 634 by 791, which is 500, around 500,000 values. Okay. And I can plot this. And this is the plot. Okay, this is the plot of the image. All right. So each pixel, if you look at some of the values in here, each pixel is a number going from 0 to 1, where if it's close to 0, it's black. Okay, and if it's close to 1, it's going to be close to white. So 0, 0 is this top corner here. So if I go to this region, say this region here, where there's kind of like a light in the background, so maybe around 200 and maybe around, I don't know, 370 or something, then we'll have values that are close to 1. So if I do, let's say 201 to 210, and let's do 371 to 380, okay? Oh, maybe I have these dimensions reversed. It's row first, then column. Okay, so these are values that are close to 1. Okay, so in this region right here where it's pretty much white, we have values that are very close to 1. Whereas in this top left corner up here, we had values that are close to 0, indicating that it's dark. Okay. So so what we can do is we can perform principal components analysis on this. Okay, we can do PCA, and we can treat this as a rather than think of it as an image, 634 by 791 pixels, right? 791 rows, 634 columns. We can treat this as kind of each column of pixels as kind of like a variable, right? So we have 634 variables. And can we reduce this down to, say, 50 principal components? So, so that's what I'm going to try to do, okay? Okay, out of curiosity, what would those values be if the image was colorful? So if it was colorful, it would still go from 0 to 1. It's just that you would have 0 through 1 on 3 channels, red, green, and blue. So, I mean, if you drop, put a droplet of water on your phone, okay, that will magnify the things, and you'll notice that that every pixel on your screen is actually made up of red, green, and blue. And just by kind of mixing how much red light, how much green light, and how much blue light there is, you can produce pretty much all the colors that we can see. And so white light is red, green, and blue set to maximum intensity. Black would be red, green, and blue set to the lowest possible intensity. Yeah, don't put it in your sink. Just one drop of water on your screen, and you should be able to see the pixels on your phone, made up of individual red, green, and blue dots. Okay, and then so bright red would be red, the red channel set to maximum, and green and blue set to the lowest. Okay, blue would be blue set to the max, and red and green set to the lowest. And green is green to the max, and red and blue set to the lowest. And then if you want something like yellow, I think you put green and blue to the max and red to the lowest. Let me see, RGB color wheel. Okay, I'm sorry, so red and green, yeah, red and, yeah, yellow is no blue. You are, yeah, that's right. Okay, so this is what you get. Yeah, so red and green mixed together makes yellow. And when it comes to light, I know, like, when you're talking about colors, there's additive and negative, and so when you're talking about paints and stuff, you know, red and yellow mixed together to make orange. But then when you're talking about light, red and green light mixed together to make yellow light. So anyway, and so all the you know, all of these things are achieved by different values of intensity. Okay, so anyway, but anyway, just to kind of keep it simple, I have it in black and white. So I have 634 kind of dimensions, and let's see what we can do to reduce this, right? So the process is we have to center our values, okay? So what I'm going to do is I'm going to take the column means, and I'm going to subtract the column means from every column of pixels, okay? And so I've subtracted the column means from every column of pixels, and in order to kind of do this in matrix mode in R, I have to transpose it, subtract the column means, and then transpose it back, okay? And so if I plot this, okay, plot as image, okay, the okay, what we end up getting is we get this image that looks kind of streaky, all right? And what's going on here is that each pixel, we've subtracted the mean color, which would kind of be gray, so that if you took the average of all of these colors, okay, if you took the average of one column, is that they would all end up having the same average here, okay? And so so what ends up happening is that spots where there was a lot of white, okay, in order to kind of compensate, these areas got this got darker, and so there, you know, we had to kind of subtract a lot. And then in columns where there was quite a bit of black, like this arm here, we had to subtract, you know, a little bit less, or maybe even add something back. And so this ends up getting kind of lighter. And so, and because we're working in columns, everything is forming a vertical streak. And so, so we're getting this streaked image where we've subtracted off the mean of each column. Okay. All right. So once we've done that, once we've centered our matrix, the principal components can be done by taking the covariance matrix, right? And so I've got a giant matrix, 791 by 634, and I'm going to find the covariance. And so my covariance matrix is going to be a 634 by 634 matrix. So if I take the dimensions of this covariance matrix, it's 634 by 634, and I can ask R to calculate the eigenvalues. So here are the eigenvalues. I can say eigen of this covariance matrix. Okay. Actually, I'm going to just go ahead and use the code that I've done here. right? And so the eigenvalues here, when you calculate eigen, you get two objects in there. One is the vector of values. You have all of the eigenvalues, of which there are 634. And then you have 634 eigenvectors, okay? And so you have your matrix of this. And so to perform principal component analysis, we just have to say, I only want to keep, let's keep, say 50 of these things, okay? So just arbitrarily, I've chosen 50, but we could have picked any other different number. And so I'm going to just keep only the first 50 columns. And so I'm going to call this PC50. And so here I can, so we now have, I've reduced my matrix from something enormous, 791 by 634, down to something, less than 1/10 the size, where it's 634 by 50, okay? And it does not make sense. Like if you try to plot this, if you try to plot these eigenvectors, they are meaningless, right? So if I try to plot, there's nothing, there's no meaning to this thing. This just represents kind of the formula or the linear combination of these things. There's no meaning here, okay? And even if I take, and so there's no meaning to this thing. And then you can take your, take the original data, or not the original, the centered data, which represents this image. So the centered data still corresponds to an image, just with vertical streaks. And I could project that data onto the first 50 eigenvectors, okay? So this matrix, okay, if we look at the dimensions of this matrix, this is 791 by 634. And if I multiply it by the principal components, which is 634 by 50, just the 50 that I've kept, the projected data is now 791 by 50, okay? Again, less than 1/10 of the original image, right? And again, this thing, it does not make sense to plot this either, all right? So to try to plot the projected data, there's no meaning here either, okay? So so this is the data when we've projected it down to 50 dimensions, okay? Which is not, it doesn't have meaning to our eyes if we try to look at it directly like this. So what we have to do is we have to reconstruct the original image, which is 791 by 634 pixels, okay? So the idea here is that the original image, which is 791 by 634, takes up a lot of space in memory, okay? The original data has 501,000 elements to kind of keep track of, all right? And the idea here is when we do dimension reduction, we've reduced it to a much smaller thing, 791 by 50, all right? So this is a lot fewer elements, and maybe I can transport, we can just take the projected data, right? So I can, if I wanted to, we could say, you know what, let's go ahead and let's delete, let's delete everything else, okay? And there would only have to be, what just happened here, okay? So what I could do is I could say, I want to delete everything. What do I need to keep? I need to keep, all right, so if I go through and I delete all of this other stuff. Okay, so now we've reduced the amount of stuff that I've stored. Okay, so I just have the projected data, the kind of the 50 principal component directions, and then kind of the original vector of means. So I've reduced this, and we can transport this, which is a lot less data to kind of transport. Can we still reconstruct the original image? Okay, and the answer is yeah. So I'm going to take the projected data, and then my 50 principal components. So these are, these matrices are a lot smaller, and I'm going to reconstruct my image. Okay, and so when I do this, what did it do? Do try catch. Must redraw. Okay, I don't know what it's complaining about. Okay, so I can reconstruct the original image or something like it. Okay, and so this is back down to a huge matrix. Okay, 500, 1,000 thing values, right? So this is 791 by 634, and we have to add back the means. Okay, and we can plot this. Okay. And so this is the image that we've reconstructed based on the principal components, right? And now if I compare that, and let me delete this, and let me delete the streaky image, okay? So this is the original image. Okay, so here's the original image, and this is what we recovered after only keeping the first 50 principal components. Okay, so I don't know how well you guys can see, but on my image there's definitely some funny patterns that are showing up, and it's not as clear as, say, the original image. The original image is a lot sharper. And here I've kept kind of the first 50 are the largest 50, the eigenvectors that correspond to the 50 largest eigenvalues. Okay, so yeah, when you run eigen on R, it's going to find all the eigenvectors, and it's going to sort them by corresponding eigenvalues. Okay, and it's going to do the largest eigenvalue to the smallest eigenvalue. So I keep the first 50 eigenvalues, and this is the image that we are able to reconstruct. Okay, which is has less contrast, but you can definitely tell that it's the same picture, right? And again, what are the values that we've stored in the in memory is just we really only had the small matrices. We did not need. Okay, so as far as the amount of data that we had to transport was this 5 kilobytes of the means, this smaller matrix, which was 791 by 50, 309 kilobytes, and 634 by 50, 247 kilobytes. Okay, so a total of around 550, 560 kilobytes. Okay, versus the full image took up 3.8 megabytes in memory. Okay, so so we definitely reduced the amount of space required in memory to construct it. Now the trade-off is that you lose a lot of the image fidelity, right? You lose this has lower contrast. Okay, and it's interesting that by keeping only 50, it's a little bit blurrier, and there's less contrast. And that kind of exactly represents the concept of keeping, maximizing the variation, right? So variation in an image, if you think about what the variation in an image represents, it means the difference between the darkest and the brightest spots on the image, right? So high variation means you have white areas that are very, very bright, and you have dark areas that are very, very black or very, very dark. Okay, and so high contrast means the difference between white and black is very stark. Low contrast means the difference between white and black is less stark, and that it's a little bit, you know, a little bit more gray and a little bit more gray. So, and that's kind of what we're seeing when we compare the image. So when you only keep the first 50 principal components, you know, you're not able to capture as much variation that existed in the original image. So, so that's what we're kind of seeing here. All right. Would this change if I did the correlation matrix instead? I haven't done the correlation matrix, so I think the results would end up being the same, because the correlation matrix, well, I don't know, maybe we would get something a little bit different. What the correlation matrix would do is we're applying it to kind of, after we basically scale each of the columns. We scale each of the columns so all the columns have the same amount of variance. So I guess technically, like if you look at the left edge, all the pixels here, most of them are dark. You know, probably the column with the most amount of variance is something here where you have both dark and both very dark and very bright elements. Okay, this column also probably has quite a bit of contrast, whereas something over, you know, on one of these other edges where all the values are very similar to each other probably has less variance. And what correlation does is it kind of scales everything so everything has the same amount of variance. So I'm not quite sure what would happen, and you'd also have to find a way to undo the scaling, so there's just more values to keep track of. So I think the results would be a little bit different. So anyway, let me go back and just load up the original. Okay. So what I did was, actually, I'm not going to go ahead. I'm not going to run this, but I said, well, what would happen if instead of keeping 50 principal components, what would happen if I keep only one principal component? Okay. What happens if I keep only one principal component? And so I did this, okay? And so if you keep only the first principal component, which means you reduced it from 791 by 634 down to 791 by 1 pixel, or by 1 column, and then you use that to try to reconstruct the image, the resulting image looks like this, okay? So this is completely unrecognizable, all right, as an image here. But this is what you get when you keep only the first principal component and you try to reconstruct it, right? So this is kind of projecting everything down to one dimension and then trying to recover the data from here, okay? When you keep two principal components, this is kind of the image that results. And so remember, what PCA is trying to do is it's trying to capture as much variation as possible with kind of the values that we have, all right? And so you can see kind of the broad structures, right? This is kind of like an abstract version of this thing where there's a bright white window here, okay? And then you got these bright white napkins here, and then you have a black dress and a black glove here. And so it kind of has captured the bright white window, this bright white area on the table, and then you kind of have some darkness here, and this is, you know, trying to capture as much variation in this picture with just two principal components. Okay, with three, it's able to capture a little bit more. Okay, we're getting a little bit more kind of this area where there's darkness, and you get a little bit of kind of the bright whites from these. I think it's a hanging chandelier or something. Okay, and as we add more, so you can just see more definition and more of the image becoming showing up here. Okay, and so now we actually get some shape to the napkins here, and something, but it's still completely unrecognizable as an image. Okay, with 6 principal components, okay, Audrey Hepburn's eyes start to emerge here, okay, because you know, her eyes and makeup and eyebrows are dark, okay, compared to the rest of her face. And so, you know, that contrast or that variation in kind of the brightness and darkness begins to show up in the image. Okay, so as I increase the number of principal components, you know, by the time we're at 10, we might recognize that there is a person's face somewhere in here. Okay, and there is some structure here. This is nightmare fuel. Okay, yeah, and so as so I'm going to go ahead and start, rather than just going up by ones, I'm going to go by 2. So here with 2 principal components, now we're starting to be able to get something a little bit more recognizable. And so I'm going to keep adding. And so by the time we get to 20 principal components, this is like, if you squint, you might say, oh yeah, these are kind of, you know, this image and this image are kind of recognizable. Like this is a very like low quality version of this, right? I think there's memes online of like what we call too much JPEG, right? Too much JPEG in that. So JPEG is what we call a lossy image compression format, in that every time you run the JPEG algorithm, you lose some image quality. And so here, you know, we're only keeping 20 of the principal components, and we've lost a lot of the image quality. This is not. I'll talk about JPEGs later, but this is not how JPEGs work. Okay, and as I increase the number of principal components, the image gets sharper and sharper and sharper. Okay, so here it is with 50, and at 70, I would say it looks pretty good. And by the time we get to 120 principal components, I would have a hard time distinguishing. Let's see, how do I zoom in here? Okay, I would have a hard time distinguishing between this image and this image. I mean, this one's still clear, but this is PCA with a 120 principal components. So we went from 634 to 120, so about one-fifth of the number of kind of dimensions that had to be kept, right? And again, something happened here. You have to reconstruct the image. Something happened with my. Yeah, 120 is definitely is way more gray. Okay, something has happened to my computer, and I cannot show. Oh, geez. Let's try this again. Not working, not working. Okay. Well, maybe extra large icons. Can I make these any bigger? Okay. Okay, there we go. So 120, 250, 300, 400. So, you know, there's more gray, and as I increase the number of principal components, you know, you get more contrast. Okay, that's basically the story here. Okay, and so between 500 and 634, the original image, and 500, there's less difference, right? As we reduce the number of principal components, okay, we're capturing less of the variation, so we have less contrast. Okay, and so I think, you know, when you hear about something like capturing 99% of the variation, 98% of the variation, this is kind of what we're talking about. So I think if I, do I have the results of Eigen? Okay. Okay, so sum of Audrey eigen $sign values total. So the total of this is this, and let me do cumulative sum. Cumulative sum divided by total. So let me do round, say 3. Okay, so when we get to, so when you have only keep the first principal component, you get around 38% of the variation, okay? And when you get to, say, the 10th principal component, you're capturing around 86% of the variation, okay? So this image represents 86% of the variation in values that appear in here, okay? And then when you go up to 20 principal components, that's around 93% of the variation, okay? And at 30 principal components, this is 96% of the variation, okay? And so, you know, you might say like, oh, 30 principal component, 96% of the variation, that sounds like we've got a lot of variation, okay? And this is kind of what it means to capture 96% of the variation. I think for image quality, we'd say, well, 96% does not look good, but you know, there's trade-offs, and maybe it doesn't matter. Maybe, you know, maybe it's good enough, maybe not, okay? And the difference between, say, 96, 97, 98, 98.5 is, so this is 40 principal components, which would be 97%. 50 is 98%. 70 is 98.8%, okay? This is the kind of the difference between 98 and 98.8% of the variation here. All right, question, is there a general way to determine how many components we should use, or is it it's completely dependent on the data? So, so you have to kind of think in your head, like, how much of the variation do I need to capture, right? And, you know, this exercise where I'm doing principal components with an image is a little silly, because this is not how we do it in real life. But it also, but because our brains are so good at recognizing images and detecting differences in images, this is what the difference is between, say, you know, 93%, 96%, and 97%, okay? And how much do you actually need to capture? And maybe it's okay to only get 86%, or maybe, or even less, right? So 6 principal components, 1, 2, 3, 4, 5, 6, around 78% of the image of the variation captured, okay? Right. Okay, so I do want to say this is not how we transport images. So probably the most common compression format online is are JPEGs, and then others are PNGs and things like that, and GIFs and things. But yeah, JPEGs use what's known as a wavelet, and they compress images in a completely different way. So theoretically, it is possible to compress images using principal components analysis, but on a practical level, it is not done because the computation required to kind of undo the image, where you have to you know, do the kind of matrix multiplication to reconstruct the image and all of that. Apparently that's not a favorable, I think that's computationally heavy and not preferred. And I don't know, there's all sorts of reasons as far as like why you wouldn't want to use this. Theoretically, you can compress images using principal components by treating it as a dimension reduction problem. but on a practical level, it's not how we do it. All right, and so when you have an image, you generally don't try to do something like this to the data, but it is kind of neat. I think it's neat to see principal components used and being able to see how keeping more and more principal components captures more of the variation that's present in the image, and what exactly it means to capture more of the variation. Okay, and and by the time we get to say 200 principal components, we're capturing 99.9% of the variation. Okay, and at 300, it's basically when you round off to 3 decimal places. Beyond 300, it says you've captured pretty much all the variation that exists in the image. And so if you can tell the difference between, say, 300, 400, and 500 principal components, that's the difference that we're talking about in terms of, is there a difference between 300, 400, and 500 in terms of the image that gets reconstructed by keeping more principal components? According to R, these are all the same when you round off to 3 decimal places. And I would say, looking at the image, they look pretty much the same to me. Okay, I can start to notice a little bit of kind of definitely, losing, at 90 principal components, it certainly seems a lot more gray. Okay, and that amount of gray basically accounts as 99.2% of the variation versus 100% of the variation. That's how little of a difference we are talking about between 90 principal components and something like this. Okay, 99% of the variation captured. Okay, which is I think a lot easier to detect in an image. Okay, because we're attuned to it, but when you're just talking about a big matrix, how much of the variation have you captured? This is what we're talking about. So anyway, this was just like I just thought was a fun little exercise to use principal components for. Again, we don't really do image compression this way. Okay. Did you guys have any questions? I was just going to keep it short today. I think the big part was going over the homework. And not the homework, going over the topics for the final exam. Question about homework 6? Okay, go ahead. What is AES? Aesthetics, I think. Is that part of the ggplot command when it has V1 and V2? Okay, yeah. So in ggplot, what you do is you assign a variable or a column, an attribute of the data to an axis or a visual property. And so in our case, I think we're going to assign variable 1 or variable 2 to the x-axis or the position in the y-axis. When it says the PC1 axis, but I can't change the name from V1 to PC1 without getting an error. Is that okay? I guess, I don't know. I'm not 100% sure if I know fully what thing you're referring to. Basically, what you want to do is when you plot the original data, it comes in at an angle, and then when you project it down, it's gonna basically rotate the cloud of points from like this to like this, and that's what I want it to be. Yeah, I don't know if you have to rename it. Can you leave it as such, or I'm not sure. All right, because the instruction file mentions file name requirement. Oh, that doesn't matter. Okay. There's no neural networks in the final. No, you guys had neural networks in your midterm. So, so I'm not going to put the neural network on the final. Yeah. Oh, I have a lecture view and quiz. Okay, yeah. Lecture view and quiz today is EBB, elephant, bear, bear. Okay, quiz answers, elephant, bear, bear, EBB. Those are the answers. Okay. Okay, that's it. Do I have office hours? I can, maybe like on, should I do it on like Wednesday or Thursday? All right, I'll do office hours. I'll designate what time. Oh, I guess I wrote it right here. Thursday, 1 p.m. That's what I wrote. Office hours. Thursday at 1 p.m. will be my office hours. Okay, that's it. Quiz answers EBB. Okay, EBB. All right, thanks guys. We'll call it early today, and we'll just end here. So good luck as you guys study, and we'll see you guys on Friday for the final.